Okay, welcome back, everyone. Any questions while we're waiting for a few more people to arrive? Okay, so let's move in the direction of the Oppenheim conjecture. And as I said, I want to spend a fair amount of time putting this in context. So let me recall what we proved last time and discuss what happens with lattices and quadratic forms in dimension 2 in detail, because Oppenheim's statement does not hold in dimension 2. And so it's interesting to know what the phenomena are, the surprising phenomena are that arise in higher dimensions. So last time we proved the following theorem. So let Q be an integral quadratic form. Q from R into R, signature PQ. That includes the statement that this is a definite form. Sorry, not definite, non-degenerate. That does not represent 0. Remember, this means that if x is in Zn and Q of x is equal to 0, this implies x equals 0. Then SOQZ, which is the subgroup of Q that preserves the integral lattice, is a lattice in SOQR. In fact, the quotient of SOQR and SOQZ is compact. Okay, so let's talk a little bit about the case n is equal to 2. The case n is equal to 2 is special for a number of reasons. One is that in dimension 2, first, the interesting case is the case where the signature PQ is 1, 1. Because for a definite form, SOQR would just be a circle, and so it's automatically has a compact quotient, even if this group is trivial. So the interesting case is signature 1, 1. So let's start with an example that's very easy to understand. How about Q of xy is x times y? So this is a quadratic form on R2. And it vanishes on the on the x and y axes. Unfortunately, it represents 0. So the theorem doesn't apply. So this represents 0, since Q of 1, 0 is equal to 0, for example. But it's a good picture to have in mind. Its level sets are hyperbolas. Here's the locus where Q is equal to 1. And it corresponds to a one-dimensional hyperbolic space. So it's like the Minkowski model, with these being the geodesics, and then the hyperbolic plane would be over here. Now, what is SOQR? These are the matrices that preserve the product of x and y, and it's a subgroup of SL2R because it has determinant 1. So how can you preserve the product x and y? Well, you multiply x by a constant and you multiply y by the inverse constant. So SOQR is actually equal to our friend A sitting inside of SL2R. In other words, it's the diagonal matrices A0, 0, A inverse. And one thing you'll notice about A, which is, of course, also isomorphic to SO11, is that it's not generated by unipotents. These are semi-simple matrices. There's no upper triangular matrices in this nice group. So this is not a group to which Ratner's theorem applies. Also, let me just remark that usually the standard inner product for the standard quadratic form alternative to this would be x squared minus y squared. That looks more like our usual picture of Minkowski space, but that's just this picture rotated by 45 degrees. So then the level sets look like this. And again, this factors as x minus y times x plus y. And so there's lots of points that represent 0. For example, all the integer points on the diagonal. So again, this theorem doesn't apply. So the interesting case is the quadratic forms that don't represent 0. Now, any quadratic form of signature 1, 1 factors over the reals as a product of linear forms. So more generally, in a general quadratic form of signature 1, 1, up to scale can be written as QAB is x minus AY, x minus BY, where A and B are real numbers. And we want it to be of signature 1, 1, that is, it should be non-degenerate. And that means we have A not equal to B. Okay, so when is this integral? Well, let's expand it out. So this is x squared minus a plus b times xy plus ab times y squared. So we want these two numbers to be integers. And that just means that, that a and b are the roots of the corresponding quadratic equation, x squared minus something times x plus something times some constant is equal to 0. So when this is integral, a and b are either rational numbers or they're the two roots of an integral quadratic equation. But if a and b are rational numbers, then this form represents 0. So when is this integral and not representing 0? This happens exactly when a and b are elements of a real quadratic field, say q adjoins square root of d. And in fact, they're both roots of the same integral equation. So b is equal to a prime. That is, it's the Galois conjugate of k. Okay, so the interesting quadratic forms are those that correspond to polynomials with rational coefficients. You see, if this is rational, then of course it's proportional to an integral. So when it is rational or integral, that happens if and only if these two roots are Galois conjugates of one another. And then the theorem says that so that if b equals a prime, then SO QZ is a lattice in SOQR. And SOQR is essentially a copy of A, as we've just seen. So as an abstract group, it's isomorphic to the real line or to the reals under multiplication. And so this discrete subgroup has to have rank 1 so that the quotient can be a finite volume, it can be compact. So now let's think about what that says in terms of our traditional picture of the upper half plane. We can describe quadratic forms by looking at the conics they define. When you have a quadratic homogeneous polynomial on Rn, its zero set is a conic or a curve of degree 2, a quadric on the projective space of dimension n minus 1. In this case, the projective space of R2 is just RP1. And the corresponding conic is just the pair of lines where the quadratic form is 0. And in that case, here, those are the lines of slope A and slope B. So we can think of QAB up to scale as corresponding exactly to the pair of points A and B on the real axis, on RP1. And then we have SL2R acting here. And the statement that SLQZ is big says that inside of SL2Z, which is the subgroup preserving the whole integral lattice, there must be a big subgroup, SLQZ, isomorphic to Z, that preserves this quadratic form and therefore fixes these 2 points. But now SL2R acts on the upper half plane as well. And if it fixes these 2 points, then it fixes the geodesic joining them. Let me call it gamma A. So when this group is a lattice, it means that this geodesic has a non-trivial stabilizer in SL2R, because SLQZ is nothing more than SLQR intersected with SL2Z. So in other words, what this is telling us is that if you take 2 Galois conjugate points on the real axis, then there is a non-trivial element in SL2Z that stabilizes them. And so the quotient of this geodesic by the action of SL2Z is a circle. In other words, this descends to a closed geodesic on the modular surface, the space of lattices L2, which is SL2R mod SL2Z, the 2, 3 infinity orbifold. So this geodesic here descends to a closed geodesic on the modular surface. So we can sum up all of this discussion as a corollary to our basic theorem on the existence of this lattice. So a corollary for n equals 2, it says there exists a hyperbolic element G in SL2Z fixing a pair of points A and B in the real line if and only if A and B lie in some real quadratic field, because I'm using capital D, and B is equal to A prime. So the easy part is that if you have a hyperbolic element, then its fixed points lie in a real quadratic field. That's because to say that you have that G fixes an element, if we look for the fixed points of G, if we've written G as, say, alpha, beta, gamma, delta in SL2Z, then to be the fixed point of this matrix means that alpha Z plus beta over gamma Z plus delta is equal to Z, which gives a quadratic equation for Z. And so Z has to be the 2 roots of that rational quadratic equation, and therefore a pair of Galois conjugate quadratic numbers. But what this theorem is telling us is the converse. If you give me any two Galois conjugate quadratic numbers, then there is an element of SL2Z that has those as its fixed points. So this characterizes the geodesics on the modular surface. The geodesics correspond to the circular arcs joining pairs of Galois conjugate numbers. Okay. Now there's another special instance of this theorem, which everyone should be aware of, which is that it ensures the existence of solutions to Pell's equation. So I mentioned this at the beginning. This is a very special case of Dirichlet's unit theorem. So another corollary is that if d greater than 0 is not a square, then the equation x squared minus dy squared equals 1 has infinitely many integral solutions. So of course, it has one integer solution, which is you can take x equal 1 and y equals 0. So 1, 0 is always a solution. But the solutions are invariant under the symmetries of this quadratic form. In fact, what we're doing here is we're drawing in the plane. So notice that what's this again factors as x minus square root of dy times x plus square root of dy. So the quadratic form here looks like this. There's a line of where x equals square root of dy, and another line where x equals minus square root of dy. And since this is not a square, there are no integer points on these lines. So indeed, this form does not represent 0. And then we look at one of the level sets where x squared equals, where the difference is 1 rather than 0. So we look at a level set, something like this. And then we see a point here, 1, 0. But the whole picture is invariant under SOQZ. That is, the ZT lattice and the equation Q equals 1 are both invariant. And so we can take this integral point and then we can move it by an element of this orthogonal group and get infinitely many integral points on this hyperbola. And therefore infinitely many solutions to this equation. Now, you might say that's not surprising because everyone knows that a conic defined over Q is isomorphic to the projective line defined over Q. In other words, it's a basic theorem that if you have a rational conic, that it has infinitely many rational points on it. But we're proving something deeper here, which is that it has infinitely many integral points. And that's not at all obvious. I mean, it's not nearly as obvious because it's not a birational invariant. Okay, and let me remark that the proof that we've given is very non-constructive. So so here's a challenge is to find a solution for d is equal to 61. And it turns out that I have the smallest solution in the course notes on page 78, and let me just say that x and y are both approximately 10 to the 10. So there's the simplest solution when d is 61 involves 10-digit numbers. And that indicates part of the power of this theorem. The proof was not that constructive. It was based on the fact that something was closed and compact, and therefore it was a circle. It didn't give an algorithm to construct these solutions, although there is an algorithm. And as a result, it didn't furnish an automatic or simple bound on the size of the solutions. And in fact, the solutions can be pretty large. Okay, so let me just mention one more corollary, is this, that whenever you have a field, a number field, you can look at the group of units, that is the integers in the field that are invertible. And another corollary is that for k is equal to q join the square root of d, sitting inside of R, a degree 2 extension of q, i.e. whenever you have a real quadratic field, you can look at the units, which are the invertible elements in the ring of integers. And the claim is that the units, at least modulo plus or minus 1, are isomorphic to Z. The group of units is rank 1, which is the biggest it can be. And these units are kind of hard to find in general, but the idea is that the units correspond to, roughly speaking, numbers like a plus b root d, with the property that the a and b are integers and the norm of this integer is equal to plus or minus 1. And the norm of, I probably should have called this, let me call this a, and call this x and y. And such that the norm of a is plus or minus 1. And of course, the norm of a is exactly x squared minus dy squared. That is the product of a and its Galois conjugate. And so the fact that we get infinitely many solutions to Pell's equation includes the fact that we get infinitely many units in these real quadratic fields. And moreover, it shows that you see the units form a group. And that group is secretly the same as this group SOQZ. Because if you take the integers in the field, they can be embedded as a lattice in R2, and you can think of that as Z2, and then when they're invariant under multiplication by units. And so that's, and they preserve the norm form. So that's, this is basically the same group as this group. They're two different ways of describing the same object. Okay. So that explains the close connection between this theorem and geodesics on the modular surface, Pell's equation, and real quadratic fields and their units. But one thing it doesn't do is tell us too much about general quadratic forms. So let me remind you what the proof was of this theorem. The proof uses two statements. The first statement is that the desired conclusion that this quotient is compact, that involves an examination of the orbit Z, which is the Zian lattice under the action of SLQR. And this whole thing is sitting inside the space of lattices of dimension n, which is SLNZ mod SLNR, unimodular lattices. And we have Mahler's compactness criterion available. So there were two steps in the proof. The first step is that because Q is integral, this implies that Z is closed. And the second statement was that since m of q, since q does not represent 0, m of q is positive. And this implies z bar is compact. So let me remind you what m of q is. M of q is the inf of the absolute value of q of x on non-zero elements of the lattice Zn. And this implication was Mahler's compactness criterion. Okay, so in some sense, to get this compact quotient, we really needed two things. We needed an arithmetic condition, which implied Z was closed, and then we needed a geometric condition to imply that its closure is compact. And we can ask what happens when we study these conditions individually, especially what if we look at quadratic forms which satisfy this property but maybe don't satisfy that? And that's where things get interesting. So now let's consider, for concreteness, a real number A, and Q of x is x squared minus a squared y squared. So x minus ay times x plus ay. And this corresponds to the geodesic in the upper half plane that goes from minus a to a. So let me call that gamma tilde. And this itself projects to some geodesic gamma contained in the modular surface, the space of lattices of dimension 2, our favorite quotient, H2 mod SL2Z. Okay, well, it turns out that the following four conditions are equivalent. The first condition is that m of QA is positive. So you can't find integers that make this form very small. There's a lower bound to how small this form can be on the integer lattice. The second condition is that gamma is bounded. In other words, gamma bar is compact. The third condition is a condition on A itself. It says there exists a constant C such that for all rationals P over Q, A minus P over Q is bigger than C over Q squared. So of course, A has to be irrational. If A were rational, then M of Q would be 0 because you could find integer solutions, integer x and y that make one of these terms vanish. But this says A is not very well approximated by rationals. And the final condition has to do with the continued fraction of gamma, of A rather. And I won't develop the theory of continued fractions in any detail right now, but let me just remind you what this means. So you start writing your number A, you write it as an integer and plus something less than between 0 and 1. Then you take the inverse of that and you write that as an integer plus something between 0 and 1. Take the inverse of that and so on. So every real number has a continued fraction expansion like this, where AIs are integers. And the claim is that for these three conditions to hold, it's necessary and sufficient that the continued fraction has the property that the soup of these AIs is finite. So only finitely many different numbers occur in the continued fraction expansion of A. Okay, so first, let me just say briefly why these things are all the same. So to say M is bigger than 0 is equivalent to gamma bar is compact. That's again Mahler's criterion. We already proved that. That's this statement here. So this we know. Now, why are these two things equivalent? Well, suppose this geodesic, gamma bar, or gamma, let's say, doesn't get too close to the cusp. That means there's a neighborhood of the cusp, let me call it N, on the quotient space, which is disjoint from gamma. And what that means is that if we look in the upper half plane, the pre-image of that neighborhood will be a family of horoballs resting on all of the rational points. The radius of the horoball resting on 0, 1, the diameter of this will be some constant c. And then the diameter of the horoball resting on P over Q, since it's invariant under SL2Z, will by an easy computation be C over Q squared. And now remember, this geodesic is disjoint from all of these horoballs. So that means as the geodesic is coming down here towards the point A, it never crosses these white regions. But you can see that for A, to avoid this region, the closest it can come to P over Q is a constant over Q squared. And that's exactly what this inequality is here. And conversely, if this inequality holds, we can draw these horoballs and we get a neighborhood of the cusp, which is avoided by gamma. So these two things are the same. And then it's a part of the theory of continued fractions that these two things are the same. If you stop the continued fraction at some point, it gives you the best rational approximation to A with a certain denominator. And this fact that these things are bounded means those approximations are not so good. It's when one of those numbers is very large that you have a very good rational approximation. If A2 was super large, then this term would be negligible, and these first two terms would get a very good rational approximation to A. Okay, so these three things are equivalent. And so they're obviously a very important class of numbers. The numbers which satisfy all of these properties only depend on A, are called the numbers of bounded type. So the set of A such that, and I can put down any of these conditions. Let me say such that M of QA is positive. Let's call this B. It's a subset of the real numbers. These are called the numbers of bounded type. Okay, now how many numbers of bounded type are there? Well, there are, in this continued fraction expansion, I can specify these A0, A1, etc. arbitrarily to be arbitrary numbers as long as I keep them bounded. For example, I could specify these AIs to be 1s and 2s. Now, how many choices are there of infinite sequence of 1s and 2s? What's the cardinality of the set of all possible infinite strings of 1s and 2s? Who can tell me? This is not a rhetorical question.
Continuum.
Louder?
Continuum.
Yeah, the continuum. It's the same as the cardinality of the whole real numbers. So there's uncountably many possibilities for the sets of bounded types. So the cardinality of B is the same as the cardinality of real numbers. And of course, this is greater than the cardinality of all of the algebraic numbers. And so there's many more quadratic forms of this type than there are quadratic forms corresponding to closed geodesics. So there's a vast number of geodesics that are bounded but not closed. The closed ones correspond to integral quadratic forms, and those can be enumerated, whereas these have the cardinality of the continuum. You can't write them down in a countable list. And in fact, it can be proved that the Hausdorff dimension of B is equal to 1. Moreover, we know that the geodesic flow is ergodic. So if you pick a geodesic at random, it gives you a dense orbit on the modular surface. So this is not the behavior of a random geodesic. So although the Hausdorff dimension is 1, the measure of this set is equal to 0. But the main point is that there exist forms in dimension 2 which satisfy this property, and they don't satisfy it because they're proportional to an integral form. They satisfy it for some other reason, that A happens to be a number that's poorly approximated by rationals. Okay, and let me just note that with this in mind, we can now characterize when a quadratic form in dimension 2 has a lower bound, when m is positive. So if we again return to Q of AB, then we have the following result. M of Q of AB is positive, where QAB of xy, x minus AY, that's x minus BY, if and only if A and B are numbers of bounded type. And that's because the asymptotic behavior of a geodesic tending to A doesn't depend on where its other endpoint is. So if the geodesic ray tending to A is bounded, and the geodesic ray tending to B is bounded, then the bi-infinite geodesic going from A to B is also bounded when projected down to the modular surface. Okay, so we have characterized when this property holds, and there are lots of Q on R2 with M of Q greater than 0 and Q not proportional to an integral form. Okay. So now I can state Openheims conjecture, which is in fact a theorem. This theorem was first proved by Dani and Margulis, and it's later subsumed in Ratner's theorem. The conjecture is that for n greater than or equal to 3, the only way you can have M of Q greater than 0 is for Q to be proportional to an integral form. M of Q is greater than 0 if and only if Q is proportional to an integral form. That does not represent 0. And so when we're trying to prove this quotient space is compact, the proof used two things. It used the fact that M of Q was positive and the fact that the orbit of, and that Q was integral. We used the fact that Q was integral to force the orbit to be closed. That condition is superfluous because whenever M of Q is greater than 0, Q is proportional to an integral form. So in particular, up to scale, there are only countably many examples of quadratic forms with this property, in large contrast to the uncountably many forms in dimension 2. And so this is equivalent to the statement that we have up here, that SOQZ backslash SOQR is compact. So that's the amazing thing about dimensions 3 or more that that follows from Ratner's theorem and gives you some idea of the power of this theorem. So if you try to write down a quadratic form in 3 variables, x squared plus ay squared minus bz squared, and you try to keep this form from getting values close to 0, the only way you can do it is to choose a and b to be rational numbers. It's kind of an amazing thing. The arithmetic trick, which works, is the only trick which works. So it's a kind of arithmeticity statement. It says a certain geometric property of Q guarantees that Q is arithmetic. Okay. So let's do the proof. So we're pretty much in the setup for Ratner's theorem. So we do need one lemma. So, well, let's do the proof, and we'll see why we need the lemma. So for the proof, we set G equal to SLNR. We let U be SOPQ. And I should say, as I mentioned last time, it's enough to do the case PQ is equal to 2, 1. The 3-dimensional case implies the n-dimensional case. So G will be very concrete. It's SL3R, and our unipotent group will be SO21. And SO21 is essentially the same as SL2R. And so, as we know, this is generated by unipotents, by upper and lower triangular matrices. So it is now a group to which Ratner's theorem applies. Our lattice, of course, will be SL3Z. And the quotient space we'll be working in is then gamma mod G, which is isomorphic to the set of uniform modular lattices contained in R3. And then what does Ratner tell us in this setting? Well, we have to analyze what groups J can occur between U and G. What unimodular groups can appear there. There are some intermediate groups, but they're not unimodular. So it turns out that, in fact, the only possibility for J is equal to U or G. So what does Ratner imply? So the first thing is we have to take our, well, let's say what it implies directly. So Ratner says if we're given X in L3, then XU bar is equal to XJ. And that this is isomorphic to J modulo gamma J. This is the intersection of the appropriate conjugate of J with gamma, which is SL3Z. And it says that this this closure is equal to this, and this quotient has finite volume. So indeed, this is a lattice. Now, in fact, in the case at hand, we already know that this space here is compact. So by looking at Lie group theory, what we conclude is that J is equal to G, or the whole group, or just the original group U. So in other words, there's only two possibilities. The first possibility is that gamma J is that J equals U, and gamma J is a lattice in J. And the second possibility is that J equals G, and X U bar is dense, is equal to the whole space, is equal to the space of all lattices. So in fact, in the Oppenheim conjecture, you get a stronger conclusion. Either the form is integral, in which case you'll be, in this case, the orbit will already be closed, or the orbit is dense in the space of all lattices, which is the same thing as to say the quadratic form. Its orbit under SL3Z is dense in the space of all unimodular quadratic forms. So, so the conclusion is just rephrased, is that either SL2Z is a lattice in SOQR, or SL3Z dot Q is dense in the space of all quadratic forms G mod U. That's the same thing as saying the orbit of U times X is dense in G mod SL3Z. And in this case, because there are quadratic forms whose 1, 1 entry is as close to 0 as you want, even though their determinant is 1, this implies that Q of the Z3 lattice is dense in R. So in other words, as soon as M of Q is equal to 0, as soon as a quadratic form represents arbitrarily small numbers, then in fact it represents a dense subset of R. And otherwise, it's proportional to an integral lattice, and therefore its values range in a discrete subgroup of R. We have this very sharp dichotomy in the behavior of quadratic forms. Okay, so this is the sharpening of the Oppenheim conjecture, which is stated here. Now there's one last step in the proof, which is I wanted to conclude that Q is an integral form. But that's not what I concluded. What I concluded is that SOQZ is a lattice in SOQR. So that's pretty close, but it's not quite the same thing. Now remember, SOQR is isomorphic to SO21, which is isomorphic to, roughly speaking, SL2R. So basically, in the first case, I get a lattice in SL2R. In other words, I get a compact hyperbolic surface from this quadratic form, which is nice in its own right. So to finish, I need the following lemma, which is that when SOQZ is a lattice, as above, this implies Q is proportional to a rational, an integral form. Okay. So how do you prove this? You have a quadratic form with lots of integral symmetries, and you want to prove that that implies the form itself is integral. So what do we know about Q? So what we know is that Q is invariant under these integral matrices. Right? Remember, this is a subgroup of SL3Z. So we can define within the space of all quadratic forms the following vector space. Let V be the vector space of all quadratic forms F on R3, real quadratic forms, such that GF, G transpose, is equal to F. all G in SOQZ. Now, the space of all quadratic forms on R3, this is just the space of symmetric matrices. So it's the 6-dimensional space. So V is certainly a finite dimensional vector space. But look at all of these conditions we're imposing on this vector space. We have infinitely many linear conditions. It might very well be that this vector space is just the trivial vector space. But it can't be because it has to contain Q. So we know that Q is in V. But we also know that these matrices are integral. So these defining equations are rational equations for the coefficients of F. So Q is in V, and V is defined over the rational numbers. Now suppose we can prove that V is one-dimensional. That means it's just the real span of a rational matrix, or it's the real span of an integral matrix, if we like, and therefore Q is proportional to an integral matrix. So all we want to show is that the dimension of V is 1. And there's a really nice geometric proof of this. And the proof depends on the fact that we understand geometrically what SOQR is. SOQR is just a copy of the symmetries of the hyperbolic plane. Now you might say, wait, I've forgotten now. Where is the hyperbolic plane in all of this picture? Well, remember, Q is a quadratic form on R3. And so the locus, Q is equal to 0, defines a conic in RP2. Because Q is homogeneous. It vanishes on a certain set of lines, and it's quadratic. So here's the 0 set of Q is some conic. C. Where does this conic come from? It comes from the one-sheeted hyperboloid associated to this quadratic form. Over R, Q is the same as SO21. So this conic separates RP2 into two pieces, one of which is a disk and the other of which is a Mobius band. In any case, in the disk piece is a copy of the hyperbolic plane. And if we take a vector in here, that is a point rather, in the hyperbolic plane, what can we say about the orbit SOQZ dot P? Let me just call that gamma dot P. Well, remember, this group is a co-compact lattice inside of SOQR. So there's this compact fundamental domain. This point orbit consists of infinitely many points, and they accumulate everywhere on the conic. C. So this conic can be reconstructed from the action of SOQZ. If you forgot what Q was, but you remember this group, what you would find is that there is a conic in the plane that's invariant under this group. The action of the group is properly discontinuous on this open set here, and the orbit of every point accumulates densely on the conic. So the topological dynamics of SOQZ picks out this conic. It uniquely determines the conic. So now suppose SOQZ was contained in SOFC for another quadratic form F. Well then, this orbit would still be discrete. It would still accumulate on a conic, and that conic would then therefore have to be the conic defined as the 0 locus of F. So the 0 locus of Q has to be the same as the 0 locus of F. And if you have two quadratic forms that define the same conic, then they're proportional. And therefore, this vector space V is one-dimensional. And that proves that that Q itself is proportional to an interval form. Okay, so that's the proof of the Openheims conjecture. Now, there are many other consequences of Ratner's theorem that I could develop, but what I'd like to conclude with is attempts that have been made to push beyond Ratner's theorem. That is, you might wonder, are there versions of Ratner's theorem that hold for groups other than groups unipotent, that are generated by unipotents? And I should say that basically, the proof of Ratner's theorem is a very, very souped up version of the proof of Hetland's theorem. The key point is, again, to do an analysis of double cosets, as we did in that case. So you might ask, is there any hope of having some sort of rigidity theorem in the sense of Ratner for other kinds of subgroups of a Lie group G? And there's actually lots of counterexamples to most of the conjectures you might formulate. But there's one conjecture that's still open, and it's a step in the direction of finding going beyond Ratner's theorem, and it's almost true. It's almost been proved, and it's probably true. So this was developed by Margulis, the conjecture, and it goes back to work of Castles and Swinnerton-Dyer in the 1950s. Has a long history. And in fact, the recent progress on it is one of the developments recognized by the Fields Medal awarded to Elon Lindenstrass. So let me say what the conjecture is. So there's two conjectures. So let me start with an old problem that is still open. Feel free to work on this. If you solve it, I will be happy to sign your thesis for you. The conjecture is due to Littlewood. It says that for all alpha and beta real numbers, the inf over integers n greater than 0 of n times the fractional part of n alpha times the fractional part of n beta is equal to 0. And here the fractional part of a real number is just the distance from x to the integers. Okay, now why should this conjecture be true? In fact, you can almost prove this conjecture. So let's first look at this quantity here. Just n times the fractional part of n alpha. So this is based on the Dirichlet box principle. If you cut the circle S1, which is R mod Z, into n boxes of equal size, slicing it at 1 over n, 2 over n, etc., and then you look at alpha, 2 alpha, 3 alpha, etc., by the time you get up to n alpha, which might be over here, you will have passed some k alpha that was in one of the two boxes adjacent to 0. And the reason is the pigeonhole principle. As soon as you have two multiples of alpha that are in the same box, their difference lies in one of these boxes close to 0. And then n times k alpha is bounded by 1, because each of these boxes has size 1 over n. So certainly k times the fractional part of k alpha is bounded by 1. So this product here is bounded by 1 for infinitely many n. Okay, so we have one sequence that's bounded a lot of the time, or at least very, very frequently, or infinitely often. And what about this sequence here? And beta? Well, beta, this theorem is obvious if alpha or beta are rational, because then one of these is 0 infinitely often. So assume beta is irrational, then again, if we pick an interval of length 1 over n, because n beta, sorry, let me just say, we pick an interval of length epsilon, then n beta lands in this interval of length epsilon infinitely often. In fact, it lands there 1 over epsilon percent of the time. So this is less than or equal to epsilon for positive density set of n. So if this is bounded and this is less than epsilon, then the inf should be 0. So the problem is just, can you get these two things to happen at the same time? And the final idea is that probably these two events are not correlated with one another. So the chances that they eventually happen at the same time after infinitely many trials is 1. So it should be a very good probability that this does happen infinitely often. Okay, so this is Littlewood's conjecture. And it's now almost a theorem. So the theorem of Einsiedler, Katok, and Lindenstrass says that Littlewood is true provided we exclude an exceptional set of Hausdorff dimension 0. So in other words, this conjecture might have some counterexamples, but for those counterexamples, both alpha and beta lie in an extremely thin set. Probably this set is empty, but the most one can prove at the moment is that it's extremely thin. It's not just measure 0, but it has Hausdorff dimension 0. So this is pretty good evidence that the conjecture is true. Okay, now, what is Margulis's theorem or conjecture? So what Margulis' conjecture can be easily described in terms of SL3R. So I think this can remain. One can formulate more general conjectures, but if you're not careful, they turn out to be false. But this conjecture is the first interesting case, and it shows every sign of being correct still. So the conjecture of Margulis says that Ratner's theorem holds for the diagonal subgroup of SL3R. So in particular, the following is true. So let A be the diagonal group, ABC, such that ABC equals 1, sitting inside of SL3R. Then any bounded A orbit on the space of lattices on L3, which is SL3Z backslash SL3R, is compact. In other words, AX bar compact implies AX. Sorry, the X should be on the other side. AX bar compact implies AX is already compact. Okay, now let me restate this in terms of Mahler's criterion. So when we discussed Mahler's criterion for quadratic forms, we used the fact that we were dealing with the group U, which was SOQR. In other words, it was the group of symmetries of some form. What we like to do is interpret A as the group of symmetries of some form. And it is the group of symmetries of some form. It might be called SONR, where N now is a cubic form on R3. So to study the action of this diagonal group, we study, instead of a quadratic form, we just study the norm of X for X in R3, which is defined to be the absolute value of X1, X2, X3. And the reason this quantity is important is that, of course, if we scale X, Y, and Z by independent factors whose product is 1, this norm doesn't change. And in fact, that characterizes the matrices which don't change this form. So N A of X is equal to N of X for all A and A. And the converse holds essentially up to sign. So that's why I think of A as being, roughly speaking, the isometry group of this form. And with that in mind, we can reformulate Margulis's conjecture in terms of something like M of Q. So in other words, we can turn this into a statement about lattices in R3. So here's the equivalent conjecture. Suppose L contained in R3, well, actually what we call it lambda, contained in R3 as a lattice. We define the norm of lambda to be the inf of the norm of X, where X is a non-zero element in your lattice. And Margulis's conjecture concerns the lattices where the norm of lambda is greater than 0. In fact, the norm of lambda is greater than 0 if and only if, when we think of lambda, which is as this point X, which is itself, after all, a lattice, the norm of lambda is greater than 0 if and only if A dot lambda bar is compact. So let's think about what it means for the norm of lambda to be greater than 0. So we have these points in our lattice, and they're accumulating on the coordinate axes if the lattice is sufficiently irrational. And so you can make X and Y very small, but perhaps at the cost of making Z large. Or the first two coordinates can be made small, but at the cost of making the third coordinate large. And so there's a little competition going on here. So the question is, when can you find a lattice such that no matter how far you go out, this triple product is always bounded below? So indeed, the first question would be, are there any lattices with this property that N of lambda is bounded below? And the answer is, in fact, there are. There's one obvious source of such lattices, which comes from number theory. So where do lambda with N of lambda greater than 0 come from? So one source is the following. So let K be a totally real cubic field. So if you like, sorry, this should have been over Q. If you like, you can think of K as being a subfield of the real numbers. And if we have an element X in this field, then there are two other embeddings of the field into the real numbers. So we can send X to X, or we can send it to X prime, or we can send it to X double prime, where these are the three roots of the cubic equation satisfied by X. And these, to say these are all real, is to say this is a totally real cubic field. In other words, it's generated by the roots of a rational polynomial, and all three roots of that polynomial are real. So then we have a map from K into R3. which sends x to three numbers, x, x prime, x double prime. And sitting inside of this field, we have its ring of integers, which is isomorphic to Z3 as an additive group. And the image of the ring of integers is a lattice in R3. That's easy to prove because the rationals, K goes to a rational subspace of R3 of dimension 3. And this goes to the integral span of a basis for that three-dimensional vector space. So every totally real cubic field gives rise naturally to a lattice in R3. Now, what's special about the totally real cubic field is that it has a norm map down to Q. And this norm map sends the integers to the integers. And what is the norm? The norm of x is just the product of x, x prime, x double prime. Or if I put in absolute values, I get the absolute value of the norm. And you'll notice that that agrees with this norm here. If I take the norm I've written down here to R, then I get a commutative diagram. And so in particular, the image of the integers gives a lattice on which this norm is bounded below. In fact, it's bounded below by 1. Because this is an ordinary integer and it's only equal to 0 when all three of these numbers are 0. So this is greater than or equal to 1, provided x is non-zero. So when that happens, I say lambda is of arithmetic origin. It comes from some construction using field theory. It's one of countably many examples that we can construct using arithmetic. And so another way to formulate Margulis's conjecture is that n of lambda is positive if and only if lambda is proportional to a lattice of arithmetic origin. And to be really precise, by proportional, I mean that there is a diagonal matrix D such that d lambda is equal to a lambda prime as above. And in fact, I should be even a little bit careful here. I should say that d lambda is contained in a lambda prime as above, because you could always pass to a sublattice of finite index, and it would also give an example like this. Okay. So I don't have time to prove any of the progress that's on about these theorems, but I can give you a hint of why Margulis's theorem implies Littlewood's conjecture. So Margulis implies Littlewood is based on the following neat idea. Suppose alpha and beta violate the Littlewood conjecture. So that means n times the fractional part of n alpha times the fractional part of n beta is greater than some constant greater than 0 for all values of n. And now we let lambda be z times the first basis element plus z times the second basis element plus z times the element alpha beta 1 as a lattice in R3. And now we try to find elements in this lattice of small norm. So let's look for a typical element in this lattice. So one element we can write down is just a multiple of this last vector. That's one of the more interesting elements. So we would have n alpha, n beta, and n. Now, if we take the product of these three numbers, we'll get something that's about n cubed. So that's not very small. How can we make it smaller? Well, remember, E1 is just 1, 0, 0. So we can take a multiple of E1 to try to make the first coordinate smaller. So let's subtract off A times E1. that will subtract off an integer a here. And similarly, we can subtract off a multiple of e2, and that will subtract off an integer b here. Now, how small can we make these numbers by subtracting off integers? Well, that's easy. The smallest you can make this in absolute value is the fractional part of n alpha. The smallest you can make this is the fractional part of n beta, and n you weren't able to change. So if you try to make an element of this lattice whose norm is small, the smallest you can make it is this triple product, which is greater than a constant, because this is a counterexample to Littlewood's theorem. So that almost proves that Margulis implies Littlewood, because this lattice, it's easy to show, has nothing to do with the lattices coming from number fields. But there's a big problem with this lattice, which is that this vector here has norm 0. 1 times 0 times 0 is 0. So in fact, n of this lattice is 0. But it's just because of these two stupid vectors here. And so there's a final nuance in the proof where you take this lattice and you start expanding these bad vectors and contracting these good vectors at the same time. That's an isometry of n. And then you take a limit of these and you get a counterexample to Margulis's conjecture. Okay, so that's just a hint of where the boundary of knowledge resides in terms of generalizations of Radner's theorem. Okay.